Okay, so this is the very first lesson of Math 30-1, and a very important one at that. It's going to be on horizontal and vertical translations. In other words, the main focus for today is we're going to know how to take a function, or rather the graph of a function, and move it left, right, up, and down. Those are horizontal and vertical translations. Now, I kid you not, this is actually one of the most important lessons of the whole year, already starting off on the very first day, because this actual idea that we're going to cover today carries forward into something like 4 or 5 of the different chapters that we deal with in this course. So in other words, today we're really laying the foundation for the rest of the course. It's an important one. Let's get going. So first of all, I know it says hand out the printed notes. We're just watching this. You can ignore. If you have printed notes for this, awesome. You can just follow along and fill in the blanks as we go. But the main focus for today is we're going to start by reviewing function notation. That's something we would have learned about back in either Math 10C or a little bit in Math 20-1. But then we're going to investigate the translations of functions. Like I mentioned a moment ago, that's moving it left, right, up and down, and so on. A little bit of a warning, I'm watching the time right now. It is going to be a long one today. I guess you can already tell by looking at how long the video is, how long it's going to be. If I'm going to guess right now, I'm going to guess it's going to be at least half an hour. Math 30-1 gets going really quick, right? It's a pretty long lesson to start off with real quick here today. But we'll see. If I end up making this lesson half an hour, awesome. I don't think I will, but let's see. I'll eat my words, hopefully. Here we go. So first of all, let's recall a little bit about function notation. A function is an algebraic expression where an x is plugged in and a y is produced. So in other words, you put in some x, you plug in whatever x you want, and y comes out. Now, we denote a function by using this notation, f of x. This just means we have a function, and inside that function, we're plugging in an x. Now, you can call it whatever you want. Oftentimes, you'll see a g of x or even an h of x or so on, right? The f, we just use f because f stands for function, right? It doesn't really matter what you use in front of it. You can use pretty much whatever letter you want. Same goes for x. Like if you were making a function of the height of something over time, maybe you'd say h of t, where t is your variable you're plugging in. You're plugging in a time, and this function is representing the height of the object. Hopefully that makes some sense. Anyway, like I said, though, this means that the function f takes in an x. In all the cases we'll deal with, f of x will be equal to y. So if you just see f of x like this, that really represents your y coordinate as well. So as much as this is bulky, don't think about it too hard. It just basically means your y, right? The f of x notation just gives us the extra information that y is actually a function. Like I said, you don't have to use the letter f. Any other letter works as well. An example of a function would be f of x equals 2x squared plus 4. You can plug in whatever x you want into that. This will jumble it all up, and it'll spit out some number, and that number is, I'm not really pointing the right way there. That number is your y, or in other words, your f of x. I always like thinking of a function kind of like a machine. You take your x, your input, you put it in, it jumbles it all up, and boom, bingo, bango, bongo, out comes your y, right? That's all a function is. Anyway, hopefully that makes some sense. Another thing we have to understand is being able to determine whether something is a function or not. One of the easiest ways to tell if something is a function is by graphing it and then using something called the vertical line test. If you were to graph a function, even if you're just to throw it in your graphing calculator, for instance, you can tell if it's a function by using something called the vertical line test, which basically just means you draw a vertical line anywhere on your function's graph. If it intersects the graph more than once, it is not a function. So if we're looking at these pictures here, the one on the top left, this is a function because you could draw a vertical line anywhere along here and it would only cross it once on each of those locations. So this one, definitely a function. Same with this little bump kind of thing right here. You can draw a vertical line anywhere you want. It's going to only intersect once. It's a function. This half circle here, that's a function because again, it's only crossing it once. This full circle though, we're in a little bit of trouble on this full circle here. If we draw a vertical line, notice it crossed here and it also crossed here. That's more than once, right? Therefore, it's not a function. Same with this one right here. Kind of looks like a quadratic that turns sideways. This one is also not a function because as you can see, we're crossing more than once. You could say, oh, well, you could draw a vertical line like right here and it would only cross once. But unfortunately, if you are able to draw a vertical line and have it cross more than once anywhere on the whole graph, immediately it's not a function. It's failed the vertical line test. One last way of thinking about this, I'm not going to dwell on this too long. if you think of a function kind of like a vending machine, where X is the button you press on the vending machine, and then Y is the candy that comes out of it. Put it this way, in this function right here, or not function rather, that we have here, if I plug in 1, sometimes I get this number up here, which looks like it's maybe like 2.5. But then other times I plug it in, I get negative 2.5. If this was a vending machine analogy, if I push button 1 on the vending machine, sometimes I get this item here, but other times I get this item here. So imagine a vending machine, if you press like button 1, and sometimes it gave you like a Mars bar, and then other time it gave you like a bag of, Lay's or something like that, that wouldn't be a functioning vending machine, right? It's not working. You're plugging in the same X and it's spitting out different Y's at different times, right? It doesn't make any sense. So it's not a function. Anyway, I spent way too long talking about that. Let's get to the real meat and potatoes of today. In order to use function notation, we have to understand that a function in itself needs to be in reference to something that's actually manageable. In other words, an actual equation. So all of the following down here in this chart are in function notation. So we say something like y is equal to f of x plus 4. It's based around this function f of x. If I just gave you this, you'd have no idea what I'm talking about. It's just saying y is f of x, but then plus 4, rather than just being f of x on its own, or y plus 4 is equal to f of x, or something, right? In order to be able to give it in relation to something else, we have to have an equation for what that function is. That has to be something that's given to you. It's not something that you can just pull out of thin air. It has to be given to you in a problem. So let's suppose we knew that f of x was x squared. This right here in this column, we have our function notation. So these right here are just representing function notation. In other words, you can have whatever function you want. In this column, however, I want us to take the fact that we know f of x actually is x squared in this case, and write this as a new simplified equation. This will make more sense as we go through it. Let's first look at this first row. Y is equal to f of x plus 4. That's our function notation. It's based around whatever f of x is. Since this question told us that f of x is x squared, all we need to do is just replace f of x with what we know f of x is equal to. In other words, x squared. So from function notation, which is more general, to equation notation, we would write that as y is equal to, instead of f of x, we'd call that x squared, and then plus 4. Hopefully you're with me so far. Let's try this next one. Y plus 4 equals f of x. Let's write that in equation notation. That would be y plus 4 equals x squared. But I really don't like having y not by itself, so I'm actually going to change this. I'm going to minus 4 on both sides. I'm going to say y is equal to x squared minus 4. That's now equation notation. Equation notation ideally should have y all by itself. Now this next one's a lot trickier. Notice this next one says y is equal to f of x plus 5. This is our function notation. So this is not even saying what our function is, right? What this means is instead of plugging x into our function, we're actually plugging in x plus 5 where x should have been. Watch what I'm going to do with this one. So if I want to turn this into equation notation, we know f of x is x squared, but we're plugging in f of x plus 5. So instead of saying x squared, I'm going to say y is equal to, replace x with x plus 5, and then squared. Now you got to be careful on these ones, right? The reason I'm writing it x plus 5 in brackets squared rather than saying x squared plus 5 is because this x plus 5 here is replacing my x directly. Now, originally in the function, x was being squared. Since I'm replacing x with x plus 5, the whole x plus 5 has to be squared. Let's see a similar one. Y is equal to f of 2x. That's our function notation. Let's change this now to equation notation. This will be y is equal to, replace x with 2x, so it'll be 2x squared. There we go. That's our equation notation. Last one here, I think, is honestly one of the more simple ones. 5 times f of x. Well, that's just y is equal to 5 times what f of x was. That's going to be x squared. So what I'm getting at here, this was maybe a little bit of a silly way of presenting this, and I apologize. What I'm getting at here is function notation is just basically a way of writing an equation based off of some unknown f of x. It's just more general. We don't know what f of x is. F of x could have been something crazy. F of x could have been like sine of x for all we know. We have no idea. We just know it was some function where we're plugging in an x. That's just an example though, right? In this case, we knew our actual equation was x squared. So when we went from the more general function notation to equation notation, we just converted our f of x to what we actually knew what it was equal to. This will become way more important as time goes on in this course. Take my word for it. So there we are. So as we progress through this chapter, you'll come to realize the benefits of each form. Right now, you probably just thought, hey, what the heck was that? Why did we care about function notation? What is going on? But let me tell you what they're kind of used for. And again, this will make more sense as time goes on. Function notation, that first one, is excellent for communicating what kinds of transformations, or in other words, changes, are being performed on an original base function f of x. So all of those things we did on the last one, whether we're plusing 4 or minusing 4 or whatever, those are actually transforming or changing our original function. If we have something in function notation, those changes become a lot more clear. Now, equation notation is important for what's hopefully a more obvious reason. That's important for actually understanding the new algebraic representation of the transform function. In plain English, that's exactly what you have. In other words, it's what you'd be plugging into your calculator. That's the simplest way we can put it. Now, generally speaking, more than just generally, I'd say almost like 99% of the time, it's really nice to start with function notation and then use that to write your equation notation. It's really ideal starting with function notation. As much as it might seem as we go through this like that's a useless step, believe me, there's certainly a lot of use behind that. So first things first, we're going to investigate a couple of translations here. We're going to start with the first form, which is y is equal to f of x plus k. That's kind of like that first one we saw in that chart there. This time, though, we're really going to investigate what's going on. Now, just by the way, before we go any further with this, it might be a really good idea if you have more than one color pen or pencil. Ideally, if you have 3 different colors, pens or pencils, that's really going to help, especially if you have the printed notes here. If you don't, though, it's not the end of the world. You'll still be able to do this just fine. Anyway, we're going to start by considering f of x to literally just be x. So f of x, the function f of x, is just x. It wants us to complete this table. In this table, I gave you 5 different values of x, and then 3 different columns here, one representing f of x, one representing f of x plus 3, and one representing f of x minus 3. What we have to do here is we basically just have to recognize that since f of x is x, we can just create equation notation for all these. So this first column, it's just y is equal to x. This next one, since we know f of x is x, we can just say y is equal to x plus 3. And then for this last one, once again, we can just say y is equal to x minus 3. So with very low effort, I just changed all of these function notations to equation notations. There's going to be a reason for that. Just bear with me. This first column, because y is equal to f of x, we're going to find the value of y here. Well, y is equal to x. X is -2. So clearly that just means y is equal to -2. In this next one, y is equal to x. Well, x is -1. Well, that means this is -1. You're probably seeing the pattern here. X is 0. That means y is 0. X is 1. Y is 1. X is 2. Y is 2. Not a big deal. Now, in this next column, a little bit more challenging, we're doing x plus 3. Real crazy surprise here. X is -2. We're going -2 plus 3. That's going to be 1. Let's do the next one. -1. -1 plus 3. Well, that's going to be 2. You might see a pattern here. 0. 0 plus 3 is 3. Hopefully you see the pattern by now. 1 plus 3 is 4. 2 plus 3 is 5. There's that column ready to go. This last column now, it's x minus 3. So if x is -2, -2 minus 3 is -5. -1 minus 3 is -4. 0 minus 3 is -3. 1 minus 3 is -2. And then 2 minus 3 is -1. Now, the reason we care about this is, it might not be obvious looking at it in a table, but if we were to change this table to a graph, like we're going to do on the next slide here, hopefully these 3 different situations will become clear what's actually happening to our graphs. So this next slide is saying, sketch the graphs of all 3 functions. Now, if you have the printed notes, you'll have your table right in front of you. I actually have printed notes in front of me as well that I'm going to rely on, so I won't have to switch back and forth. But I'm going to do these 3 different graphs in 3 different colors. I'm going to start by graphing that first column, which was just y is equal to x. If we plug in the points that we had on there, we knew when x is -2, y was -2. So there's a point right there. You'll want to follow along, by the way, and this is where you'll probably want your 3 different colors. -1 is our x, and then -1 is our y, and then we had 0, 0, and then we had 1, 1, and we had 2, 2, and you can see how that pattern is continuing. Now, this is going to be a little tough for me using my my pen tablet, so I'm just going to kind of continue the pattern and hopefully be able to get this to line up. Believe me, it is a lot harder than it's going to look here, but I'll do my best at getting as straight of a line as I possibly can here. That actually isn't too terribly bad. There we go. Now I'll finish the line over here as well. Always draw your line as long as you can on your graph. So there we go. Y is equal to X, my first column. That one's all ready to go. Now, as for the next one, it wants us to graph the f of X plus 3. I'm going to do that one in blue. So once again, I'm going to look back at my table from before. Actually, I will switch back here. I'm going to look at my table from before. I'm graphing these ones right here. So when X was -2, we found that Y was +1. So I'll plot that right there. When X was -1, we found Y was +2. When X was 0, we had 3. When X was 1, we had 4. And when X was 2, we had 5. You can probably see the pattern there. I'm just going to continue that chart each way. That should be good enough. And then I'm going to try to draw that as straight of a line as I can. Oh, no, already not doing a good job. Let me try that again. Draw it as straight as I can. Ooh, I'm being a little wobbly, but I'm doing my best. Best is always enough here. That's what I think, at least. Maybe that's just my excuse. Pretend that that's as straight of a line as I can get going here. A little bit wavy. Again, that's way harder than it looks. On yours, you should hopefully have a ruler or some other straight edge. But that's the graph of our f of X plus 3, or in other words, in equation notation, X plus 3. You might be seeing already what's happening here. I'm going to graph the other one, though. Last one here I'm going to graph is this one in green. That was our far right column. When X was -2, Y was -5. So I'll plug that there. When X was -1, Y was -4. When X was 0, Y was -3. And then we had these other couple points. Again, I think you have the idea. I'm just extending this so it's a little easier for me to graph. Here we go. Another straight line. Do my best. Here we go. This one seems to be going a little better than the other one. Let's hope I didn't just jinx myself here. There we go. Awesome. Oh no, I just deleted it. How did that happen? Okay, try that again. Yes, there we go. Now we're good. Now we're good. Awesome. All right, so let's answer these questions on here. How does Y equals f of X plus 3 compared with Y equals f of X? So in other words, how does the blue one compare to that red one? Well, it might not be perfectly clear to some of you, but others you might actually see it. What ended up happening was each of those points we had, and again, it was like this point to this point and this point and this point, etc. Each of those points just moved up by 3. So I'll even write that. They moved up by 3. Interesting. They moved up by 3. I wonder where that comes from. What about this other one? How does f of X minus 3 compare with the original f of X? So how does the green graph compare to the red one? Well, look at those 5 points again. Which way do you think they went? Scratching my head here. Moved down by 3. So in other words, this whole idea of adding or subtracting something on the outside of our function notation, that causes something to move up or down. So that answers this next question here, the effect of k. If we had y equals f of X plus k, generalize a rule about the effect of k? Well, the effect of k is it's a vertical translation. A vertical translation is just a fancy way of saying it moves up or down. So maybe I'll even write that. It moves up or down by k. And if I'm going to elaborate on that even more, if k is positive, in other words, if we're adding k, it goes up. And if k is negative, of course, it goes down. So if you have plus negative something, or in other words, minus something, your graph is going to go down. That's the effect of k. So in other words, if you have something in function notation where you don't actually fill in whatever f of X is, and you have f of X plus k, you know that your function, whatever your function may be, is going to be moving up or down by that value k. F of X could be whatever you wanted. It doesn't just have to be X, or it doesn't have to be X squared or anything simple like that. F of X could be literally any kind of function you can think of. It could even be like a crazy quadratic, like what we did back in Math 20-1. Simply just adding or subtracting something on the end of it after the function actually moves that function up or down. Kind of cool. But anyway, we're going to move on. We have another kind of translation we got to go over today. We're making reasonable time, but we're still 20 minutes into this. It's going to be a very long lesson. Let's now consider x squared as being our f of x. This time around, we're also not only just changing what our base function is equal to, we are also changing the fact that we're not adding something to the outside of the function. We're actually changing something on the inside of the function. These are a little weird. Let's start, before I complete this table, let's start by turning all of these function notations, where y is listed in reference to an f of x, let's change them to equation notation. We know what f of x actually is. It's x squared. So on this first one, we can say y is equal to, instead of f of x, we can say it's x squared. That one was pretty clear. This next one's a little weirder though. Notice it's x plus 2 inside the function. That means the x inside the original f of x is being replaced by an x plus 2. So this is going to become y equals, instead of writing x, I'm going to write x plus 2, and then it needs to be squared. This last one here, f of x minus 2, same idea. We're replacing our x with an x minus 2. So this becomes y equals x minus 2 squared. Now let's plug all these things in here. So let's start with negative 2. If I plug negative 2 into this, negative 2 squared is going to be 4. Negative 1 squared is going to be 1. 0 squared is going to be 0. 1 squared is going to be 1. And 2 squared is going to be 4. As for this next column, it gets a little weirder. Negative 2 is our x, so we have to say negative 2 plus 2 and then squared. Well, negative 2 plus 2 is 0. 0 squared is 0. Now let's do negative 1. Negative 1 plus 2, well, that's 1. 1 squared is 1. What about this one? 0. 0 plus 2 is 2. 2 squared is 4. 1, if we plug that in there, 1 plus 2 is 3. 3 squared is 9. And then 2. 2 plus 2 is 4. 4 squared is 16. Whew, that was pretty speedy. What about this next one? X minus 2 squared. If we plug in negative 2, negative 2 minus 2, well, that's negative 4. Negative 4 squared, that's positive 16. What about negative 1? Negative 1 minus 2 is negative 3. Negative 3 squared is 9. 0. 0 minus 2 is negative 2. Negative 2 squared is 4. 1. 1 minus 2 is 1. 1 minus 2 is negative 1. Negative 1 squared is 1. And then 2. 2 minus 2 is 0. 0 squared is 0. Hopefully that wasn't too quick for you, but it is, again, just calculation. So it's just a matter of plugging these values of x into each of these equation notations that we set up. So really important to understand, function notation is what I gave you. Equation notation is what we change it to, understanding that f of x is truly just x squared. Now, as you probably saw coming, we're going to sketch the graph of all three of these functions. This one's going to be a little weirder. Again, you'll probably want to have 3 different colors, pens or pencils. I'm going to switch back to red. I'm going to do y equals x squared as being my red function. The points that we were given were negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Now, if you're really keen, you might actually remember back in Math 20-1, we graphed these x squared functions, they're called quadratics, by using something called a 1-4-9 rule. That's where you went from your vertex down here, you moved over 1 and then up 1 times a, and then over 2 and then up 4 times a, and then over 3 and then up 9 times a. So I actually know that my next one is going to be 9 on both sides over here, and I'm just going to draw that in just to help guide my graph a little bit better. So if I'm going to connect these dots, this one's not linear, so it doesn't have to be a straight line, but I want to get the curve as nice as I can get here. That was reasonable. It could have been better, but not too bad. That was pretty good. This one's always tough. There we go. Got it. Perfect. So x squared is done. Next one I'm going to do, I'm going to change to blue. I'm going to do the x plus 2 squared. So again, that was x plus 2 squared is the one I'm going to graph. This time I'm going to rely on the points that are on my table from before. So again, I'll just flip back so you can see it. I'm going to rely on the points in this column right here. So when x was negative 2, y was 0. So I'm going to plug that there. When x was negative 1, we had positive 1. When x was 0, we had 4. When x was 1, we had 9. And then when x was 2, we had 16, but that's off the chart, so I'm not going to graph that. If I connect these dots here, you're going to see a graph kind of like this. Oh, that was miserable, but you get the idea. And hopefully what you also see is this is just one of the arms of this quadratic. It's like there's a missing arm over here. You could probably guess by plugging in negative 3 into that and all that, like negative 3 plus 2 would be negative 1 squared, which is 1. So we put a 1 there. Or you can just understand this is going to be a symmetrical graph. So this 4 over here needs to come over here. And this 9 needs to come way over here. So it is a symmetrical graph. I'm just going to complete it so it looks a little nicer. If you didn't get that, it's just a review of quadratics. Quadratics need to be symmetrical. That one's pretty bumpy. I didn't really draw it the best, but hopefully you get the idea. I'm going to switch back to green now. I'm going to do this one. That's the x minus 2 squared one. I'm going to do that in green. Once again, I'm going to rely on the points on that table. At -2, we're at 16. That's off the chart, so I won't worry about that. At x is -1, we're at 9. So there's that. When x is 0, we're at 4. When x is 1, we're at 1. When x is 2, we're at 0. We can connect those dots because that's all we really had on that. It's, again, a weird arm there, doing my best. And once again, as you probably could guess, it is going to need to be symmetrical. So I'm just going to move this dot over here. This dot can come over here, and then this dot can come over here. So there we are. That's going to be a more symmetrical graph. Good enough for me. Now let's talk about how these relate to the base function. We'll focus on that blue one first, where we had f of x plus 2. This time around, I think it's actually a little more clear what's happening to this graph. Remember, the red function was our base function. That's what we're basing everything off of. F of x plus 2 looks like it moved it to the left by 2. So I'll even write that. It moved left by 2. As for f of x minus 2, that one looks like it moved right by 2. Now that's kind of interesting. I don't know about you. Like, again, maybe I won't speak for everyone, but for me, when I hear plus, I think more positive. So I think it would move to the right. And when I hear minus, I think more to the left. Like, I think left is more of a minus direction. But in this, when we're doing function transformations, it's actually kind of backwards. When you have f of x plus 2, that's moving it to the left. If you have f of x minus 2, that's actually moving it to the right. Kind of a little weird, a little bit unexpected in my opinion, but just something you got to watch for. So if we're going to sum up the effect of h here, relative to the graph of f of x, generalize a rule about the effects of h in y equals f of x minus h. So this is what we would call a horizontal translation. In other words, it moves left or right by h. Now, this is where we have to be really picky. Notice it says relative to the graph and f of x minus h. If h is positive, and bear with me on this one, believe me, if h is positive, in other words, we have an x minus a positive h, then it moves right. What we saw before was we had x minus 2 as being our translation there. We're saying that h in that case was actually positive 2. Yes, it's minus, like x minus 2, but the h value in that form is positive 2. That's what's moving it right. Now, if h is negative, in other words, we have x minus negative h, or in other words, minus a negative is x plus h, then it moves to the left. Printing here is terrible. I'm trying to be quick. That's why. So do you notice anything backwards about this type of transformation? I would say that if you have a quote unquote positive h, gives you actually truly an x minus h, and it moves it therefore to the right. So a positive h is actually giving you x minus h, and that's a movement to the right. So it is a little bit weird. It's a little backwards. Most people feel that way. Some people go like, I don't know what you're talking about. I feel like that's not really that unusual at all. But unfortunately, it's just a hurdle that you have to get over. Just understand that if it's x minus h, you're going to the right. If you see x plus h, you're actually going to the left. However you want to remember that, that's on you. Okay, so next page here. When you're graphing transformed functions, it's usually easier to have a solid understanding about the shape of a base function. A base function is, again, just something that we've given you. That's something that we're basing our function off of. It's usually something very simple, something like f of x is x, or f of x is x squared. The equation of a transformed function can look very intimidating. However, if you can identify the base function by stripping away any of the added fluff, you can determine what transformations were applied to that base function and then go from there. In other words, sometimes I'm going to give you something crazy, and we'll deal with that in just a little bit. Sometimes I give you the actual equation rather than starting in function notation, and you might go, what on earth? Where did he go? Where did he go from there? If you just kind of strip away all the weird adding and subtracting stuff that we put on there and just figure out what kind of function we were working with in the first place, that's actually usually a lot easier so you can think about what's actually happening, especially if you know what that base function looks like. Let me show you what I mean. There's a bunch of different base functions we'll see. So these first three are some very common simple base functions. The one on the far left there is just f of x is x squared. If you strip away all the fluff, like the adding and the subtracting, and you just have an x squared in there somewhere, you know your original base function graph looks just like that, just like a quadratic. So in other words, like a U or an upside down U shape. Another type that we're going to see quite often is an x cubed graph. Now these are new to Math 30-1. You didn't see these in Math 20-1, so this is going to be a bit of a new one for you. But an x cubed graph just kind of looks like a big twirly, like twisted bow tie kind of look, right? And if you want to really compare it, you can see like when you have like x is 1, we have y is 1. And then if you had x is 2, it'd be 2 cubed, so it would be way up at 8, right? So it really shoots up really fast. But another thing that you're going to notice is that it actually goes down into negative territory as well. And this is because if you had like -1 cubed, that's -1 times -1 times -1. -1 cubed is actually -1 itself. So just watch the shape of that graph. You'll need to know what that shape of the graph looks like because we'll be using it quite a bit. Another graph that we'll see is the square root of x. Square root of x just kind of looks like a quadratic that fell onto its side and then lost one of its arms. That's a very common graph we'll see. Some other ones we'll see. The one on the left is a nightmare. That's 1 over x. That was a whole unit back in Math 20-1, but I wouldn't blame you if you've forgotten it by now. These ones are by far the toughest of them all because they've got quite a crazy shape. But here's a huge hint for you. If you're ever given a 1 over x graph as your base function, just focus on your vertical and horizontal asymptotes. A vertical asymptote was like an invisible or often dotted line that your function just doesn't touch. It just comes really close to, but it doesn't actually touch it. And same with a horizontal asymptote. It's just a horizontal line that your function doesn't touch. So if we took this function and moved it left, right, up, and down, really, if you just focus on moving your horizontal and vertical asymptotes left, right, up, and down, you're going to be in a lot of luck. And then basically you just note where those asymptotes meet and you just go over one, up one, and that's where we have a definite point. We'll do an example like that later today, but they're really strange. As for this next one, f of x is the absolute value of x. We saw a little bit of this back in Math 20-1, but these are pretty cool. They're just basically a big sharp V shape. They do come around every now and then, but it is what it is. Speaking of which, every now and then, literally write the next slide. So describe the transformation and sketch. So we have y equals the absolute value of x and y equals the absolute value of x plus 5. I'm going to start by graphing this one right here. Matter of fact, I'm going to change back to red just for, just for old time's sakes here. Here we go. There we go. So I'm going to do this one in red. The absolute value of x is just a pointed shape. So when you have x is 1, y is going to be 1. When you have x is 2, y is 2, x is 3, y is 3, and so on. Same with if x is 0, we have 0. If x was -1, then the absolute value of -1 is +1. If x was -2, the absolute value of -2 is +2, and so on. So you get that nice V shape. I'm really going to make this Mickey Mouse here. Oh, this is miserable. Oh, that's really bad. Oh, well, you get the idea. Anyway, what's more important is this one right here, this y equals x plus 5. Now, y equals x plus 5, think about the transformations that have been happening to this. Notice that we've got this plus 5, but notice where it is in the function. What we've dealt with so far is we've dealt with where we have f of x plus k, but we've also dealt with f of x minus h, like this. Notice on f of x plus k, these were our vertical transformations. That's on the outside of the original function. This one right here, where we have f of x minus h, that's a horizontal transformation, and it occurs on the inside of the function. Where do you think this transformation is, this plus 5? Do you think it's on the outside of the function, or do you think it's on the inside of the function? Well, hopefully you see, since it's within these absolute value bars, this is actually embedded inside the function, so it must be a horizontal transformation. Now, since it's x plus 5, do you think it's going to move left, or do you think it's going to move right? Think back to what we did just a moment ago. Well, since it's x plus 5, as backwards as that might seem, it's actually going to be moving left 5. So the easiest way of doing this transformation, rather than making a whole table and plugging in values and going to town on that, is just take your original base function, this really horribly drawn pointed V that I did here, and just move all of the points that you put on there to the left by 5. So I'm going to start with this one right here because this is one of my better ones. Move it to the left 5. 1, 2, 3, 4, 5. There's that point. Same with this one. 1, 2, 3, 4, 5. There's that point. This one goes over here. This one goes over here. And this one goes over here. You probably can see the pattern. So I'm going to do my best on this one to draw it. That was reasonably okay. What about this one? Oh, no, that's where I lose out. It seems to be the ones, I guess you can probably tell I'm right-handed here. So going backwards is a bit tough. There we go. All right, so that one's all ready to go. That has all been dealt with. So in other words, we noticed since it was x plus 5 inside the function that we were moving it to the left by 5. All right, we got a few more that we're going to do here. Actually, quite a few more, but we'll get there. We'll get there. I told you it was going to be a long lesson anyway. All right, next one. Describe the transformation and sketch. We have y equals x cubed and y plus 3 equals x cubed. This one's weird right here. This is really weird. Y plus 3. Why don't we change that right away before we do anything? This is going to be y equals x cubed minus 3. We always like having y by itself. So I think we could probably describe the transformation first of all. Remember, if it happens on the outside of a function, it's a vertical transformation. Whereas if it happens on the inside of a function, it's a horizontal transformation. So looking at this minus 3 we have here, do you think that's on the inside of the function or do you think that's on the outside of the function? Well, hopefully you see it is actually on the outside of the function. So we know this is going to be vertical. Now, if it's vertical, that means it's either going up or down. Do you think it's up or do you think it's down? Well, vertical ones are actually quite nice. Vertical transformations, because it's minus 3, this is actually going down 3. Now, the base function we're working with here is this x cubed. So I'm going to start by drawing x cubed. I'll do this in red. Okay, so y equals x cubed. Well, I know if I plug in x is 0, we have y is 0. If I plug in x is 1, 1 cubed is just 1. If I plug in 2, 2 cubed is 8. Notice how much that shoots up so quick. We should go to the negative side now. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. And I'm going to tell you right now, that's as many points as we can actually plot on that. So I'm going to do my best to draw this. These are really tricky. Again, it kind of looks like a twisted bow tie kind of look here. There we go. This part's the best part. It goes all like swivelly. Swivel and then swivel. And then we'll see if we can go up. Good enough. There we go. And then a little further. Perfect. Awesome. All right. So that's our y equals x cubed. Now, as for this other one, I'll switch back to blue. We already determined that this function is just moving our base function down by 3. The easiest way to do this is just to move it point by point. Pick the points that you plotted on there and just move them down by 3. This one down here is going to be a little tough. Technically going from negative 8 down 3 brings us to negative 11. I will plot it anyway, just for fun. This one moving it down 3, not a big deal. It takes us to negative 4. This one over here becomes negative 3. This one becomes negative 2. And then this one way up at 8, that just drops down to 5. Now we can kind of clearly see a bit of an outline of our blue graph. So just do your best to draw it. We moved it down by 3. It's a little bit tricky, this part right here, but do your best. And then this is the part that I really like because it goes kind of like a swivel, swivels here and then swivels up. And then it's going to shoot all the way up this way. Perfect. And then it's going to keep on going. Notice we want to try staying below our original red graph as much as we possibly can. So it was a little bit exaggerated there, but hopefully you get the idea. The key word on all these questions, just by the way, before you criticize my drawing ability too much, keyword here is sketch, right? We're not going for picture perfect or anything, but I want to see that you at least understand the thought process here. If something's happening on the outside of the function, it moves up or down. If something happens on the inside of the function, it's moving left or right. All right, so this next one's more interesting. Sketch the graph of y equals x minus 2 squared minus 3. This time around, I didn't tell you what the base function is. The base function is the function by which we are basing all of our transformations off of. The good news is, oftentimes a base function can be pretty clear to identify. If you stripped away all of the weird stuff happening to this function, what kind of a function do you think you'd be left with? Well, by the weird stuff, really, I just mean this minus 2 and this minus 3. If you removed those, you'd be starting with y equals x squared. That's a function that we hopefully understand how to draw. You could actually, as a matter of fact, draw it right on here if you wish, right? You don't have to. I'm not even convinced that I will on this one. But we know what this function looks like. It starts at 0, 0, and it does the 149 rule thing, and it just makes a bit of a U shape right there, right? Now, if we're to look now, compared to this, what kind of a transformation occurred on this? I want you to notice that we put a -2 inside the function. That's going to be our horizontal translation. Since it's on the inside of the function, it's going to be moving it either left or right. Now notice it's x -2. If there's a -2 on the inside of the function, did that move it left or did it move it right? Well, remember, these ones are a little backwards. This one actually moved to the right by 2. Now the thing on the outside here, that's going to be our vertical transformation, the -3. These ones are a little more predictable. Since we moved right 2, and then we have a -3 on the outside, that means we moved down 3. So what you can do is you can just take your original x² function, and if you want to draw it just for the sake of having it there, go for it. But you just have to take that x² function and move it right 2 and down 3. Now I know an x² function is starting at our vertex, which usually is 0, 0. But if I'm moving all my points right 2 and down 3, I'll just start with that vertex. It's going to move right 2 and then down 3. So our vertex is actually going to be there. Everything else about the quadratic is going to stay the same, right? So in other words, we go over 1 and then up 1. And then we go over 2 and we go up 4. And then we go over 3 and we go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And since it's an x² function, we know it's symmetrical. So I know this is going to go over here. This point is going to go over here. And then this point is going to go way over here. So then I can just sketch the graph here as much as I can. Again, I'll do as good of a job as I hopefully can do here. There we go. And then same with this on this. And then keep on going. Perfect. Right. That's all we got to do on that one. So as long as you have a sturdy understanding of what your base functions are, drawing these is often not the end of the world. Now I say that, and then we get to the beefcake question of the day. This one is the absolute boss of today. This one is as tough as it gets. Sketch the graph of y minus 5 equals 1 over x minus 2. Holy smokes. If you saw this an hour ago, you'd go, what on earth? Maybe you're even saying what on earth right now. I don't know. Let's first start by getting y by itself. Add 5 on both sides. We got y equals 1 over x minus 2, and then plus 5 over here. Okay? At least y is by itself now. That's a little easier. Now, this question, just like the last one, we didn't give you a base function to work with. This is where you have to strip away the nonsense and think, what kind of a base function are we working with? Well, if you took away this whole -2 and this whole plus 5 business, you could hopefully see that we have y equals 1 over x. 1 over x is one of our classic common base functions that we'll be dealing with. But unfortunately, like I mentioned earlier, I would argue it's one of the toughest ones. This is that function that has your vertical and horizontal asymptotes. So what I'm getting at here, how about I actually just roll back real quick? This is the function right here that we're going to be dealing with. What I'm getting at here is instead of worrying about like plugging in different values of x and all what, let's just think about moving these vertical and horizontal asymptotes by whatever our transformations are on this question. If you look at this question very carefully, you're going to see right where our x is, here, we have x minus 2. I would call that the inside of our function. It's right up close and personal with where our x is. And since it's a -2 inside of the function, do you think that moved it left or do you think that moved it right? Well, remember, when you're inside the function, that's going to be moving it to the right. So we're moving this function right 2, and then this plus 5 is just chilling on its own on the outside of this function here. So that's going to be moving it up 5. So what we need to do, I'm going to scroll all the way back in. What we need to do, there we go, is we need to take our vertical asymptote and move it right 2. And we need to take our horizontal asymptote and move it up 5. Let's see if we can do this. So usually our vertical and horizontal asymptote are just our x and y axis, but I'm going to move it right 2. So I'm going to have a vertical asymptote just to the right by 2. These I usually take my time, just get that dotted line drawn in there. There we go. And then I'm going to take my horizontal asymptote and I'm going to move it up 5. So I'm going to have something along the lines of this. Now, the other thing, I'll just go a little further there. There we go. The other thing that you'll notice with these, if I go all the way back, compared to where our asymptotes meet, we actually have a definite point over 1 and up 1 from that centerpiece there, and then also over 1 and down 1 from that centerpiece there. So if we go back and look at our asymptotes, if we go over 1 and up 1, we're going to have a point right there. And then if we go back to our centerpiece here and we go over 1, down 1, we're going to have another point right there. As for the rest of this function, it's just doing that thing where it hugs our vertical asymptote up and our horizontal asymptote this way. And it does not need to be super pretty. Same with this one over here. It's going to go down this way, hugging that vertical asymptote, but never actually crossing it. That was really not pretty, but you get the idea. And then same with this way, it's going to hug it, but never actually touch it. Perfect. Those are the worst ones, but you still need to know how to do them. They do show up every now and then. Whew. All right, we're almost done here, folks. Believe me. All right, here we go. All right, so determine the equation of the transformed function in bold. So what that means is this one on the left, because it's not bold, is the original. So this is the original. And we moved it over here to the bold one. Now it does give us a little note here, just use function notation. In other words, don't worry about making a literal equation notation. I know it says equation here, but we want it in function notation. So if this original is our f of x, how could we express what happened to turn that into this bold function? Well, think just in words, what happened to this function? How did we move it? Clearly, we didn't move it up or down, but we did move it to the right. Now, how much did we move it to the right by? Well, focus on that vertex piece. I think that's probably the easiest piece to check. We went from here, and then we went over 1, 2, 3, 4, 5, 6, 7, 8. So we went right 8. Now, in function notation, to move right 8, that's a horizontal transformation. So that's going to occur inside the function itself. That's going to be f of x minus 8. So that right there is going to be our function. And if you really wanted to go crazy, you can say y equals f of x minus 8, but it's up to you. You can even just say f of x minus 8. That works just fine. So we moved it right 8. That is our function notation for that one. What about this one? Maybe you'll even be able to try this one on your own. Notice it's not only going up, but it's also going over. So there's going to be a vertical and a horizontal transformation here. This is our original f of x. The bold one is our transformed one. Well, let's see if you can beat me to the punch here. Think about how much it's going up by. Think about how much it's going over by. Remember, if we're using function notation, horizontal stuff happens inside the function. So maybe you want to start there. If we're talking about how much it's going over horizontally, it looks like it's going over 1, 2, 3, 4 places. So it's going right 4. Again, see if you can beat me to the punch here. And then it's going up 1, 2, 3, 4, 5, 6, 7. So it's going up 7. So since it's going right 4 and up 7, always start with your horizontal stuff here. We're going to have y equals f of x. Now, is it plus or is it minus? It's going right. Well, it's going to be minus, so it's minus 4. And then the stuff that makes it go up and down is on the outside of the function. Well, it's going up 7, so that's going to be plus 7. So f of x minus 4 plus 7. Whew, we've covered a lot, but we're almost there. Home stretch here. So last couple examples, write the equation in the form y equals f of x minus h plus k. Kind of weird wording here because this is a function notation, but it gives us the equation itself. I think it actually wants us to write the equation. So it is kind of strange. What I would do on this question, just to like ease any, ambiguity about it, is I would write this in both function notation and equation notation. So let's actually just do both. This first question says f of x is 1 over x, and it's transformed 3 right and 2 down. Let's start with function notation. So function notation will literally just look like this. So y equals f of x minus h. Well, this is our horizontal transformation. We moved right 3, so that's going to be x minus 3. And we went 2 down, so that'll be minus 2. There we are. That's our function notation. Now, just to get this as a home stretch kind of idea here, we'll also do equation notation. That's where we actually use our real equation right here. So since we're going to actually use our real equation here, basically what that means is if you look at our function notation, x minus 3, just replace your x with an x minus 3, and then stick a minus 2 on the outside. So watch me do this. It's going to be y equals, replace our x with x minus 3, so it's 1 over x minus 3. See that? I replaced x with x minus 3, and then minus 2 chilling on the outside. This equation I just wrote here would move that function right 3 and 2 down. What about this next one? Notice this function is a very strange base function. That's really weird, but we can still manage with it. Take my word for it. We're transforming this right 4 and down 2. With such a strange equation like this, it's really important that we start with function notation on this, because otherwise it becomes a lot more difficult than it needs to be. Hopefully this will really ring it true. So starting with function notation always looks like this. This is what's so nice about it, right? So it's going to be y equals f of x. We're moving right 4, so it's x minus 4. And then down 2, that'll be minus 2. In terms of equation notation, this is where things get trickier. Remember, you replace x with this x minus 4 here. There's still a plus 3 down here. Don't worry about it. That plus 3 is just going to stay there, right? So we're going to replace x with x minus 4. This is going to look like this. Y equals 1 over, instead of x, it's x minus 4. Then there was still a plus 3 there, so we'll say plus 3. And then minus 2 is chilling on the outside, so we'll just put minus 2 over here. Now, if you really wanted, you could say that was it for that one, but I could clean this up. Let's be nice here. Let's actually clean this one up. This is y equals 1 over minus 4 plus 3. So negative 4 plus 3, that's negative 1. So this is x minus 1 and then minus 2. That's what that one would clean up to. And that's just nicer cleaning it up, so it's not as weird as it would be otherwise. So again, what I really want to drive home on questions like this is, even if you're asked to make an equation, start with your function notation, which will always look like this. It's really safe. You just have to understand what your right or left transformation is, as well as what your up or down transformation is. Once you have your function notation, then go to equation notation. It becomes a lot easier if you do it in that order. Final question of the day. We swear on this one. This is it. Last one. I'd be really impressed if you pause this video here and give it a try. I know we're already over 50 minutes in. I told you it was a long one today, but we are going to get this done. So f of x equals square root x. We're transforming this 3 down and 2 left. That's a little funny. We swapped the order here. This is our vertical and this is our horizontal. Remember, horizontal has to do with h and vertical has to do with k. Be careful here. Let's start with function notation. With function notation, it always looks like this. So it's going to be y equals f of x. We're going to the left. That's our horizontal. Is it going to be plus or minus? Well, left is plus, so it's going to be x plus 2 because we went 2 left. And then we're going 3 down, so that's going to be minus 3. Boom, that's our function notation right there. That one's done. Now we go into equation notation. This is where you look at what that x plus 2 business is here. That's what we're using to replace our x. So anytime you see an x, we're going to replace it with an x plus 2. So this is going to be y equals the square root of, instead of x, we're going to write x plus 2. And then minus 3, like I always say, just chilling on the outside. It's doing its own thing. It's not underneath the square root. It's literally on the outside of the whole thing. That's our equation. So if you wanted to see this function transformed 3 down and 2 left, this bad boy right here is what you'd be plugging into your graphing calculator. Holy smokes, that was a long lesson. That's about as long as they get. I apologize for that. If you stuck through the whole way, that's me clapping right now. Well done. You did an awesome job. But just to add more fuel to the fire here, here's a handful of questions just out of the textbook. Page 12, questions 1, 4, 5, 6, 7, 9, 11, and 18. You are going to need practice at this. Believe me, as long of a lesson that was, you do need to get some practice. Anyway, if you need any help, please let me know.